name is Sinclaire Manning. I just finished up my second year of grad school in the astronomy department at UT. And thank you very much. And tonight I'll be telling you all about observing the invisible universe and how we can accomplish that through multi-wavelength astronomy. So maybe the first question we can ask right off the bat is, what does it mean to be invisible? And so, or what makes something invisible? And we have many examples of this in science fiction, pop culture, fancy aliens with their cloaking technology. James Bond did a little bit better than Wonder Woman in terms of being invisible. Or maybe if you have like a magic ring or a magic cloak, that might help you out a little bit as well. But I'm going to pick a really simple definition for what makes something invisible. And so to be invisible, it means that you're not perceptible by the human eye. So right away, I'm talking only about humans here. And I'm not talking about things that are really small or too far away to see, because you can use microscopes or binoculars or telescopes to aid you with that sort of thing. But what I'm really getting at is what the human eye is sensitive to on the electromagnetic spectrum. So if we take a look at the electromagnetic spectrum, this is showing the range of electromagnetic radiation that is flowing all around throughout the universe. And so starting on the left-hand side with the shortest wavelength, highest energy radiation, and then moving to the right, you go to longer wavelengths and lower energies. So you've got gamma rays and X-rays, ultraviolet, and then you get to this tiny sliver, and in this tiny sliver is what's known as the visible wavelengths. And that's what we can see as humans. And then as you move on to longer wavelengths, you get into the infrared, microwaves, and then radio. So if you look at the axis here, you can see the wavelength scale ranges an order of like 15 magnitude, from 10 to the minus 11 to 10 to the 3 in meters. And we are capable of seeing 400 to 750 nanometers. So we're missing a ton of the electromagnetic spectrum when we're only looking with our human eye. And I'm sure there's, a lot more to be said about why our eyes work the way we do, something about cones and rods or stuff like that, but I don't know. So anyway, so what do we do when we only have our human eye to work with, but we want to see other parts of the electromagnetic spectrum? We build instruments that can do it for us. So this plot kind of has a lot going on, but I just want you to take note. So we flipped it now, so we have shorter wavelengths on the right and longer wavelengths on the left. So yeah, first let's just take a big shout out to say thank you to our Earth's atmosphere for protecting us for these really high energy, short wavelength radiation. Gamma rays would all be like a bunch of Hulks walking around here if they could get through. X-ray and ultraviolet, a little bit ultraviolet can come through our atmosphere. That's why we all wear sunscreen in the summer, especially here in Texas. Optical is no problem getting through our atmosphere. Infrared, the shorter side of infrared does okay, but when you get to longer wavelengths in the infrared, actually the water vapor in the atmosphere starts to take it out. So then you got to go outer space to start viewing that. And then radio is really unbothered by anything, and you can take radio observations all day, all night long. Of course, you do have to worry about all the man-made interference, anything like a car, an airplane, a satellite, a cell phone, wireless internet. All of that will interfere with your radio signal, so you got to be careful. So, okay. For my own research, I primarily focus on longer wavelengths, and I think they're really cool. So I'm going to go ahead and tell you guys about them today. So we're going to start with infrared. And so infrared can actually be broken up into 3 main spectral regions. You have near infrared, which is about 0.75 to 5 microns, mid-infrared, 5 to 25 microns, and far infrared from 25 to 35 microns. All these are all kind of merged together a bit, so don't take these markers too seriously. It's just like a rough estimation. And I'm not going to actually talk too much about infrared, though, because I know our next speaker, Dr. Kim Sokol, is going to be talking to you about infrared. But the main point I want to get across here is what you're able to see in the infrared that you can't see with your human eye. So in the near infrared, you're going to be able to see cooler red stars, dust that normally blocks out light to our eye becomes transparent and you can see through it. Then as you go to the mid-infrared, you can start to see thermal radiation from planets and comets and asteroids. You can see dust that's been warmed up by starlight. And then as you go to the far infrared, then you're getting to really cold gas. So as you go to longer wavelengths, you're tracing colder objects. So if you see, like, the temperature here is 5,000 all the way down to 700 Kelvin, mid-infrared 790 Kelvin, and then far you're tracing really cold things, 90 to 10 Kelvin. And again, those are all, you know, they kind of blur together a little bit. That's a basic kind of ruler you can use. And as you saw in the other graph, when you get to these longer infrared wavelengths, those start to be absorbed by our atmosphere, so you need space observatories to observe them. Okay, so let's look at an example here of why we love the infrared so much. So does anyone know what this is? There we go. Everyone knows this one. It's a beautiful Hubble image, Pillars of Creation in the Eagle Nebula. This was taken from Hubble. This is in optical filters, so visible light that we can see. You see these beautiful columns of dust. And you can see some stars, but they kind of look, you know, kind of red, which would mean they were a bit older, maybe smaller. But you think, oh, it's a really pretty picture. Cool. But recently, Hubble went back with their near-infrared camera and took a new picture of the Pillars of Creation. And it looks like this. Yeah, that was the reaction I was looking for. So yeah, that's kind of different. So if we look at them side by side, you can see, as I mentioned with near-infrared, you're getting rid of all this, and you're not getting rid of, the dust is still there, but you're able to see through a lot of the dust. Only the densest regions of gas and dust are still block our vision from what's underneath. But you can see a lot more cooler red stars have popped up out of nowhere, and then the stars that we thought were red initially, if you can find their companion on the other side, now look a lot bluer, and you realize, oh, no, these are actually a lot of young stars that were born in this nebula, and then you can see through to where the really active star formation is taking place. So before you didn't know anything that was happening over here, but thanks to infrared, you have a much clearer picture of everything that's going on. All right, so now I'm going to move on to radio, and forgive me if we have any microwave fans in the house. So now it's really cool. Yeah, so what is radio astronomy? Is there anyone in the house who thinks this is what radio astronomers do? If you do, it's totally fine, because there aren't that many cultural representations of radio astronomers out there. But yeah, if you don't know, this is Jodie Foster in Contact, which is actually pretty scientifically accurate. She's trying to find aliens, and she's listening to her radio signal, which in the movie it kind of works out, but in real life, radio signal is much lower than what she's listening to, and there's no way you can listen to it through all the white noise of, the satellites and cars and everything that I mentioned earlier. So, if you take anything away from this, don't think of Jodie Foster. Okay. Okay, so here's an example of some radio telescopes. They kind of come in a couple different varieties. You have giant single dishes. This is the Green Bank Telescope in West Virginia. This is in a completely radio quiet zone. It's really quiet if you like, not having internet and meditating a bit. Um, then you have the Arecibo Radio Observatory in Puerto Rico. This one makes me feel like we're in a sci-fi novel because I think it's crazy looking. It's just like in the side of a hill somewhere in Puerto Rico. This is the Very Large Array in New Mexico. Jodie Foster was in front of this in contact, so that was kind of cool that they were in the right location. But so this is a large array of telescopes. And then I threw in E. Merlin down here because this is actually the radio array that I use in my own research. And it's got 7 radio dishes spread out through the UK. And so if you have like a super long baseline like this, and the larger they're spread out, the better resolution you can get in your images. So anyway, that gives you an idea of what radio telescopes are like. So what would happen if you took this 100-meter dish and replaced your eye with it? What would the night sky look like in radio wavelengths? Well, it turns out that it would look a little something like this. And it doesn't look too crazy. There's some point sources. If you can kind of see, there's kind of a concentration of things in this band. Can you tell me what this band is? Yeah, it's the Milky Way. This is what the Milky Way looks like. This is from Green Bank, West Virginia. If you were observing with the Green Bank telescope. But yeah, some interesting points. These like brighter points are the coolest thing I find in these. If you can take out these little rings, bubbles, and then you get to those on. They're supernova records that you see in radio waves. So yeah, if you've never been, if you want to see it, like here today, you can see the pulse structure. If they do, it's like these points are not stars. They're actually distant quasars. So they're super bright galaxies that are really bright radio fields. And yeah, you're definitely not seeing this stuff. And radio observations are awesome. They can tell you like all of these things that visible wavelengths. Okay, so look at infrared, then again you're peering through these dust lanes, and these knots show where star formation is taking place. And now the far infrared, not the greatest resolution, but it still tells you something. The far infrared is tracing your dust distribution as a whole. So you have a lot of dust right in the center of your main galaxy. You have dust in your 2 major arms. And then you got a lot of dust in your companion galaxy as well. So it's still telling you something. And then radio similarly kind of traces the same structure. A lot of activity towards the center where you might imagine a black hole is. And then X-ray, I think a lot of these points are also background sources. And I read that this point right here is a background quasar. It's not actually part of the galaxy. And they weren't sure what this one was, which was interesting. And I don't know if that mystery has been solved yet. All right, one more. Let's look at Centaurus A, one more galaxy at least. This one's pretty cool because if you look in the visible, I don't know, it looks kind of weird. You're like, that's not a spiral galaxy. It's not an elliptical galaxy. So they called it a peculiar galaxy, which is fair. And yeah, in UV, you're totally blocked out by this big dust lane here, but you do see emission from, newborn blue big stars. Near infrared, you kind of see through the dust a little bit, and again, it just like shows that there's this clear, like smooth elliptical structure in the middle, but yeah, how do you get this massive dust lane across? And then mid-infrared, you're tracing the dust, and you can see this nice dust plane, which is normally what you'd find in a regular spiral galaxy. And then you look at radio and X-ray, and you're like, what the hell? Is this the same galaxy I'm looking at right now? This is one perpendicular to the plane of the dust, and where's the rest of it? But so after looking at all these different wavelengths, it was decided that this was the merger of a spiral galaxy and an elliptical galaxy. And because of this extra gas and dust coming in, it set off a supermassive black hole in the center, created an active galactic nuclei, and accreting all this extra gas and dust, and began shooting off these ultra-relativistic jets out into space perpendicular to the plane. And so X-ray also kind of traces that jet for you. So yeah, super cool stuff and things you would never know if you just had this picture to go off of. Or even if you only had one of any of these pictures to go off of, really. Okay, and the last one I'll leave you with is the Crab Nebula, and I actually showed this picture a few months ago during Astronomy in the News when it first came out, but I like this one just because not only do you get your individual components, but then they also combined it into a nice full composite for you. So 5 different observatories took images of the Crab Nebula in X-ray, UV, optical, infrared, and radio, and when you put it all together, you get this awesome photo, and you just get so much more information. You can see a lot more substructure that you couldn't see before, and I don't do research on nebula, but I don't know, it's like a great candidate to say this is why it's so important to look at multi-wavelength astronomy. So hopefully I've convinced you all that if you want to know the most about an astronomical object, you really have to look at the entire electromagnetic spectrum, because you never know what you might be missing. Thank you very much.
All right. Thank you, Major Merger. We have time for a few questions. All right, we're going to start in the back.
Yeah. Oh, sorry. Repeat the question. So for Centaurus A, how do you know you're not looking at it from the side? So like you're saying this dust banded, but if you were looking down on it, then you could see more of the spiral structure of it, kind of. Yeah. I believe we are looking at it from the side, but because of the mid-infrared, and it's like a little more extended, and I'm sure they did velocity measurements on it to see if it was like rotating at all, and you could see if it's moving away from you and get like a more 3D picture of how it is. But yeah, the consensus was that it was a spiral and an elliptical merging together. But yeah, that's a good point.
All right, we're going to work away front. You, sir?
Were there 3 bands of infrared because of Because there are 3 instruments? Why aren't there 4? I think it's already... I could make a joke, or I could try to answer. Yeah, I don't know the historical reasons behind why we've only stuck with 3. Maybe they realized, okay, we're getting a little crazy over here. Because astronomers still will just say infrared, and they could mean anything. Oh, yes. Okay, so yeah, certain instruments do only look at near infrared. Like what Kim's going to be talking about is near infrared. Am I correct in that? Yes, thumbs up. And then like Spitzer Space Telescope is more mid-infrared. So yes, different, and that one's out in space, whereas IGRINS is able to do it down on the Earth because near infrared can penetrate through the atmosphere. So yes, it is. Different instruments do observe the different 3 bands. Yeah.
Okay, I'm going to go down in front first.
On that line that showed all the frequencies that started at gamma and then trailed off on radio.
Yeah.
Does that actually end on either side, or is that just what we can measure? Like what's before gamma?
Oh.
What's the starting point, and when does it end on the other side? Does it just go on?
That's when the aliens come in and tell us. That's as far as I know it goes. I have not heard of anything short word of gamma ray or long word of radio.